Ever wondered how geologists find valuable mineral deposits hidden deep within the earth? It's not just about digging randomly. It's a high-tech treasure hunt that combines geology, chemistry, and powerful statistics. Today, we are diving deep into the fascinating world of geochemical exploration and uncovering the secrets hidden in the data. First things first, you can't interpret data without a solid foundation. This means two things: understanding the geology and trusting your data. Before any analysis begins, geologists build a conceptual model. What kind of deposit are we looking for? An orogenic gold system? A VMS deposit? This model sets the stage, telling us which chemical signatures or elemental associations to expect. For instance, in some regions, gold mineralization is a complex mix of different systems, requiring a nuanced approach. Geochemistry isn't just for finding ore. It helps us reconstruct ancient geological conditions, like the temperature and pressure when a rock formed. Just as crucial is data integrity. In modern geochemistry, we're dealing with incredibly sensitive measurements. The tiniest contamination can completely throw off our results. That's why strict quality control from start to finish is non-negotiable. We need to ensure our data is both precise and accurate. While traditional methods exist, they can sometimes fall short. With geological data, a more robust measure, like the average coefficient of variation, helps us monitor precision even when the data isn't perfectly behaved. Now, let's talk statistics. Geochemical data is special. It's what we call compositional data. The numbers represent parts of a whole, like percentages. If you just plug these raw numbers into standard statistical software, you're likely to get misleading results. This is because the values are relative. If one element's concentration goes up, others must go down to maintain the total. This interdependence can create false correlations. The solution? We need to transform the data. This is where the centered log ratio or CLR transformation comes in. It's a mathematical key that unlocks the true relationships between elements. Instead of looking at absolute concentrations, we look at the ratios between them. The CLR transformation takes our constrained data and moves it into a space where standard statistical tools can be used correctly and effectively. It's particularly useful because its principal component analysis is equivalent to a more complex log ratio analysis, saving a ton of computational effort. Once our data is transformed, we can start the real detective work, finding elemental associations. Geological processes that create mineral deposits rarely leave just one element behind. They produce a whole suite of associated elements. We use techniques like principal component analysis or factor analysis to group these correlated elements together. Imagine sifting through a complex stream of data and pulling out distinct groups that tell a story. To make sure these groups are genuinely related to mineralization, we can use a refined technique called staged factor analysis. This process iteratively filters out weaker elements until we're left with a strong multi-element signature directly linked to our target. Each of these final factors represents a specific geological process. In stream sediment data, for example, these factors can actually outline the main mineralized zones on a map. The real magic happens when we connect these elemental associations to the ore's origin, or what we call orogenesis. The specific group of elements we find acts as a chemical fingerprint, pointing directly to how the deposit was formed. Let's look at some examples. For volcanogenic massive sulfide or VMS deposits, we expect to see high levels of zinc, copper, and lead, but also a unique cocktail of trace elements like arsenic, selenium, cadmium, and tellurium. The chemistry of pyrite, a common sulfide mineral, can even tell us more. Pyrite in zinc-rich zones is enriched in tin and antimony, while pyrite in copper-rich zones has more cobalt and arsenic. The element thallium is a fantastic pathfinder for zinc, as it behaves similarly during formation, helping us distinguish valuable ore zones from barren rock. What about gold? In a mixed system like the Alut region in Iran, which is both orogenic and intrusion-related gold, factor analysis was key. It isolated a specific factor with a very high loading for gold, along with arsenic, manganese, and molybdenum. This confirmed the presence of a mixed system and highlighted the power of specialized statistics in untangling complex geological histories. For massive porphyry copper deposits, we look for a different signature. We see elevated concentrations of tellurium, rubidium, copper, gold, and mercury, which reflect the hydrothermal zoning around the ore body. Interestingly, some elements like manganese and lead are often depleted in the rocks directly above the deposit, providing another clue. These patterns are a direct result of the intense alteration processes that form these giant systems. Beyond elemental concentrations, we can use isotopes for even deeper insights. Isotopic analysis is like a geological DNA test. Sulfur isotopes can tell us if the sulfur in a sulfide mineral came from a magmatic source or was derived from seawater. Carbon isotopes help trace the origin of carbon in a hydrothermal system. And radiogenic isotopes, like lead and strontium, provide fundamental information about the source magmas and the tectonic setting, helping to classify and understand different types of deposits. The final step is to bring everything together in a predictive map. We can't just rely on one layer of information. We use advanced techniques like fractal modeling to separate meaningful anomalies from background noise without having to PRE treat the data. Then, we integrate these refined geochemical maps with other data layers, like geology and geophysics, using multi-criteria decision-making. Expert knowledge is crucial here to weigh the importance of each layer. The end result is a mineral prospectivity map that pinpoints the most promising areas for exploration. When we compare a map created from a single element, like gold, to one generated from a statistically derived multi-element factor, the difference is night and day. The factor map aligns much more closely with known mineral occurrences, proving the power of this comprehensive approach. So, interpreting geochemical data is like conducting an orchestra. A geoscientist listens for the specific combination of elemental instruments playing in harmony. This multivariate symphony reveals the underlying geological processes, guiding us directly to the source of the treasure. It's a journey from raw numbers to a deep understanding of orgenesis. Thanks for joining us on this deep dive into geochemical exploration. If you found this fascinating, be sure to like, subscribe, and hit that notification bell for more content on the science of our planet. See you next time.